In today's video, we're going to talk about a theorem that goes by the name of Stokes Theorem. Now, several days back, we had Green's theorem, which saved us by turning evil, complicated line integrals into much simpler double integrals. And this theorem is similar to Green's theorem in spirit. It's going to give us a way to translate between line integrals and surface integrals and convert between those two. That way, if one of those integrals happens to be difficult and we don't want to take the time to do it, we can convert to the other, and potentially the other one will be easier than the first. So our goals for today are we need to build up a little bit of terminology in terms of positive orientation of a curve that bounds an oriented surface. There's an orientation of the boundary curve that matches the orientation of a surface, and we're going to need to talk about that. Then, once that's done, we can state Stokes Theorem, and then we'll be able to use Stokes Theorem in a couple of examples to convert between line integrals and surface integrals. So to start, suppose we have a surface S with a boundary curve. For example, a hemisphere. So let me give you an example, a picture of such a surface with a boundary. Let's call this S. This surface has an edge, which I'll draw in white down here at the bottom. And this edge of the surface is the boundary curve, which is referred to as C in this problem. Now bear in mind, there are some surfaces without boundary curves. For example, the hemisphere has no boundary. It doesn't have an edge, it's just one closed surface. As well, something like the torus, our donut from before, this has no boundary. But here, this surface drawn below, a hemisphere or something of that general shape, has a boundary curve, which is called C. Now, when we are talking about curves and parameterization of curves, curves have an orientation. They can be traversed in two different directions. And surfaces also have an orientation. They have two sides to them, and a choice of one of those sides is an orientation of the surface. Now suppose that you have chosen an orientation of the surface. Maybe I will indicate it with this blue normal vector here. In that case, there is an orientation of the curve that is match to the orientation of the surface, a matching orientation. And to find the matching orientation, which is sometimes called the positive orientation of C, we use the rule given here in cyan. If you traverse C in the positive direction, with your head pointing toward the normal vector of the surface that you've chosen, the surface should be on your left side as you're going around the boundary curve in the positive direction. So taking, for example, this surface here, if I go around the boundary curve in the direction indicated by the arrows that I am drawing, and I keep my head pointed upward in the direction of my choice of normal vector, then the surface is visible on my left side. And on my right side, I just am looking into space. So I'm moving forward, my head is pointing up, and the surface is on my left side. And that remains true no matter where I am on this curve. I'm looking forward in the positive C direction, and the normal vector is on where my head is pointing, and the surface is on my left side. Whereas, if you go and you change the orientation of your surface and you flip it upside down, it will cause the orientation of the boundary to flip as well. So that in this case, as you walk forward with your head pointing in the direction of traversal, then the surface will be on your left side. Excuse me, I just drew this I just drew this red arrow backward. The surface, if we're looking inward, we would see the surface if we are looking inward. Okay. Now, it can also be easier to remember this in terms of a right-hand rule, especially when the surfaces are upside down, as the one is here on the right-hand side. For the right-hand rule, the thing that I like to remember is that you have your thumb pointing to the normal vector, and you have your index finger pointing in the positive c direction, then your middle finger, curved in toward your palm, will point to the surface with your right hand. With your index finger pointing in the direction of the white vector and the thumb pointing in the direction of the pink vector, then your middle finger will point in the direction of the red vector, which is inside to the inside of this bowl, which is where the surface lives. So I apologize for that. We had the red vector backwards a few seconds ago. All right. So now we've established that, let's go ahead to state Stokes' theorem. So we have a surface S and a boundary curve C, and both of this surface and the curve are oriented in such a way that the orientations match according to the right-hand rule that we gave above. And we have some three-dimensional vector field, which we call F, which is behaving nicely. Its component functions have continual partial derivatives. If all those conditions are satisfied, then the following equation holds true. If you want to calculate the surface integral over the surface S of the curl of this vector field, then you get the same result as if you calculated the line integral of the regular ordinary vector field over the boundary curve. So these two quantities are equal and interchangeable. And in this video, we will see examples both of converting from a line integral to a surface integral and converting from a surface integral into a line integral and moving backward. So let's consider the following problem. We have the vector field f of x, y, z, which is given in components by x squared z, x, y, z, and sine of x, y, z. And let's let S be the part of the cone z equals square root x squared plus y squared under the plane z equals 3, oriented in the positive z axis direction. So while I have that in my mind, I'm going to go ahead and draw the surface. We have their cone z equals square root x squared plus y squared. Let me just shade in the cone here. And then the boundary curve is the one living up here at z equals 3. That circle living at z equals 3. Now they've come in and told us that this surface should be oriented in such a way that the normal vector chosen at every point should be the one pointing in toward the positive z-axis. So let's just take a moment and see if we can figure out what corresponding orientation that would induce on the boundary curve C. All right. Now notice that if our head is pointing in the direction of the positive z-axis, then the surface is located off in the direction of this red arrow. The other direction points toward empty space, and the cone itself would be in the direction of the red arrow at the point. So we want to make sure that that red arrow is on our left side as we are traversing this boundary curve C. And if we move in the direction indicated by the arrows that I am drawing now, if I move in that direction along the C, curve C, then indeed the red arrow pointing toward the surface will be on our left side. Or put another way, if you put your thumb on the blue arrow and you let your index finger point toward the white arrow, then your middle finger will curl in and point toward the surface in the direction of the red arrow. So here is the orientation of the boundary curve that corresponds to the given orientation of this surface. All right, now having just written that down, let's go ahead and have a look at the problem. It says, by any means, calculate the surface integral of the vector field curl F. Now, I'm looking at this vector field F, and just the thought of calculating its curl fills me with dread because of how complicated and how involved this vector field is. And if calculating the curl is already complicated, this question is going to get much, much worse after we still have to parameterize the cone and find the cross product and then dot it with the curl and then actually integrate it. There would be a lot more work to do after finding the curl, and finding the curl is already hard enough. So instead, by Stokes' theorem, I'm going to switch over to calculating the line integral over the boundary, because if nothing else, that allows me to bypass having to find the curl of this vector field. All right, so step number 1 is we're going to need to calculate a parameterization of C. We're going to need to find a parameterization of C, and in order to get that, I think I'm going to try and draw another depiction of the parameter C. The view that I get looking top down at the boundary curve C, with the positive x on my right side and positive y on the top. Now have a look at the orientation arrows that we have drawn. If I am traversing the boundary of C in the positive direction, these arrows are curling up from the positive x direction toward the positive y direction. And so to match that, on this 2D drawing, I'll have to curl from the positive x direction to the positive y direction. All right, the matching orientation. So this circle is being traversed counterclockwise, and let's think about its radius. This circle lives at the level z equals 3, and so if I replace that in the cone equation, I get 3 equals square root x squared plus y squared for the boundary. And based on that, this is going to be a circle of radius 3. So a counterclockwise circle of radius 3, we have a nice standard way to parameterize that, which is that x of t can be 3 cosine t, y of t can be 3 sine t, and then let's think about the z coordinate. Now for every single point on this curve, the z is constant at a level of 3, and so the z parameter can be set to a constant value of 3 as well. All right, now that we found our parameterization, our next task is to find the velocity vector for our parameterization. X prime, for example, x prime being negative 3 sine t, y prime, for example, being 3 cosine t, and the derivative of the constant z is just 0. So here is r prime. And the next thing that we need to do is we need to take our vector field f, whose line integral we're calculating, And I need to replace the x's and y's and z's in this formula with the x's, y's, and z's for our parameterization. So we have x squared z, we have x squared z, so I'm going to call this f with the parameterization plugged in. We have x squared 9, 3, 27 cosine squared t. We have x, y, z, so 27 cosine sine. And the next thing that we would need to do is we would need to replace the x and y and z in this z component for the vector field. But that's going to be really complicated, isn't it? You're going to have a sine with a cosine and a sine inside of it. Very, very complicated. So let's think ahead a little bit. Let's see if we can save ourselves some trouble. In the very next step, to calculate a line integral, we're going to need to take f of r of t and take the dot product with the velocity vector. This is how we calculate line integrals. So whatever goes in this slot, no matter how complicated it is, in the dot product, it's just going to get multiplied by the 0 in the z component of the velocity vector. So what is here doesn't actually matter, because in the dot product it's going to vanish no matter what. And so we can save ourselves a little bit of time here. So let's continue. We now have the product -3 sine t, 27 cosine squared t, which becomes -81 cos squared t sine t. We have the second product, 3 cosine, 27 cosine sine, which is 81 cosine squared t sine t. And then the third product is 0 no matter what. Okay, but have a look at what's going on here with these first two terms. They're identical except they have opposite sign. And because of that, they're going to completely cancel out. That means our line integral is going to be the integral from start to finish of just this constant 0. But if you integrate 0, you're definitely going to get 0 as a result. And so that gives us the value of our line integral, and hence it gives you the value of the surface integral. But from time to time, you will save yourself some trouble calculating a line integral by turning it into a surface integral. And that's what this next example is all about. A particle moves along the polygon with vertices 1, 0, 0, 1, 2, 1, 0, 2, 1, and 0, 0, 0 in that order. Alright, so here's my sketch. I'm going to make it right away. So here is 1, 0, 0. Somewhere up here is 1, 2, 1. Move straight back, you get to 0, 2, 1, and then back down to the origin. So it looks like this particle is moving along the boundary of a rectangle. And indeed, the hint says, notice that this polygon bounds a part of the plane with the equation z equals -1/2 y. So this flat surface, which is being enclosed by the curve that's being described here, this surface S is given by the plane z equals -1/2 y. Now they tell me in particular that this polygon is being traversed from 1, 0, 0 up to the point 1, 2, 1, back to the point 0, 2, 1, down to the origin in this general order. So let's try and think what the orientation of the surface would have to be to match the given orientation of our boundary curve. Now, we're moving along the curve in this forward direction, and we need to keep the surface on our left. So if we have our head pointing in the upward direction, as indicated by this pink arrow, if we keep our head upward, then the surface will be on our left as we move around this boundary rectangle. Okay, all of that was just note keeping. Now, as this point moves, this particle moves, it is acted upon by the force field whose equation is given here. F of xyz equals z squared 2xy 4y squared. And by any means, calculate the work done by the force field on the particle. Okay. Now, our definition for work done by a force field on a particle moving around a curve C was the line integral over C of the force field. But imagine what work you would have to do to actually calculate this value. Our curve C here has 4 corners, and so it would take 4 separate line integrals in order to calculate the total work done, because we would need 4 different parametrizations to capture the movement of this particle, one for each side, one for each piece of our boundary curve. So instead, by Stokes' theorem, we're going to try to see if it will be any easier to calculate the double integral over the plane of curl F. Calculate that surface integral. Let's see. So to begin with, let's write down what the curl of F would be. Let's calculate curl F, which is equal to the nabla operator cross product F, which is equal to the determinant of the matrix I, J, K, with partial x, partial y, and partial z in the second row, and the components of the force field in the third row. So we have z squared, we have 2xy, and for our final component, we have 4y squared. All right, so let's do some arithmetic. We've got, for the x component, partial with respect to y is 8y. And for our other product, we have 2xy partial with respect to z, which vanishes. So it doesn't have an effect. In the j slot, we have the partial of, with respect to x, of 4y squared, which is 0. Take away the partial with respect to z of z squared, which is negative 2z, and then you make it opposite because we're in the j position. And then for k, we have the partial with respect to x of 2xy, minus the partial with respect to y of z squared. So that will close that up quite nicely. All right, the next thing that we're going to need is a parameterization for this plane. And notice that the plane is being described as the graph of an equation z equals some function of x and y. And so we can take our standard parameterization, where we have x of u and v, represented by u. We have y of u and v, represented by v, and z of u and v, represented by our formula, with u in x's place and v in y's place. Then we have r sub u, which is 1, 0, 0. And we have r sub v, which is 0, 1, minus 1/2. So let's go ahead and calculate the cross product, ru cross rv, which is going to be the determinant of the matrix ijk, 1, 0, 0, 0, 1, minus 1/2. So 0 in the x position, positive 1/2 in the y position, 1 in the z position. Now let's just take a quick moment and let's make sure that the normal vector that we got here, the normal vector to the surface that we got from the calculation really does point up. It really does point up. So here, the normal vector, here's the normal to surface. And we can confirm that because the y coordinate and the z coordinate of our normal vector is positive, both of these are positive, our normal vector does point up the way that we thought it should when we were thinking about the orientation of S that matches the boundary curve. So this is the correct orientation. Yay! Alright, so the next thing that we need to do is take the dot product of our vector field curl F with our cross product ru cross rv. So we have curl F, dot product with ru cross rv. And taking that one component at a time, 0 times 8y contributes nothing. 1/2 times z is z. And then 1 times 2y, we get 2y. Alright, so next thing we need to do is we need to replace the z and the y with their parameterized versions. We could as well have replaced z and y with their parameterized versions here in the curl equation. But z was parameterized by -1/2v, and y was parameterized by v. So we have 3/2 v for the curl of f dot product with the normal vector to the surface in parameters u and v. Alright, almost there folks, stay strong. We have the double integral over the set of all u's and v's of 3/2 v to calculate. And in order to calculate that, we're going to have to rewrite this as a double integral. Now let's look at this plane and let's think about the set of u's and v's / x's and y's, which would be valid here. We have this slanted rectangle, so to speak, and we have x coordinates which are running from 0 to 1 here. And since x is being represented by u, that likewise is going to be the range of values for u. We also have y coordinates, which are ranging between 0 and 2. And since y is being represented by v, those are going to be the limits for v as well. So let's integrate this function, 3/2 y, 3/2 v, as u goes from 0 to 1, and as v goes from 0 to 2. Now the u integral of this quantity will just be quantity times u. And when we finish calculating that, we have again 3 halves v, which we need to integrate from 0 to 2. And then we have 3 over 4 v squared, evaluated from 0 to 2. And if we plug that in, we get the unassuming number 3.